Very good morning, friends. We were dealing with various aspects of retrosynthesis. You have seen the guidelines to be followed for following the order of events. As we know that order of events plays a very important role because the one group which is already present in the molecule will affect the reactivity of the molecule. Not only that, it also affects the orientation of the incoming group. That's why we have to look at the relationship between the groups and we have to add the group which directs the incoming group to the right position. And we have seen various guidelines regarding this. Today's subject of discussion is one group and two group disconnection. If a molecule has two parts in it and these two parts are connected through an heteroatom X, it has two parts and these two parts are connected through an heteroatom X. In that case, you have to disconnect that molecule next to the heteroatom. This is the general philosophy followed. This philosophy of disconnecting next to the heteroatom applies and works best for the formation of esters, amides, ethers, sulfides, etc. For example, I can take a propanil weed killer and explain this. This is propanil weed killer, propanil amide, derivative of dichlorobenzene. Here, this has two parts. This is one part, and this is another part, and this is connected through the heteroatom NH. As per the guidelines, we have to disconnect this molecule adjacent to the next to the heteroatom. I disconnect it over here. When I disconnect, the carbon nitrogen bond breaks that I am representing over here. CN disconnection. One part I'll get the amino derivative of dichlorobenzene. Amino directly I cannot add. That's why I do fragment group interconversion. I'll get nitrodichlorobenzene. I will do CN disconnection and I'll get dichlorobenzene. I take dichlorobenzene, nitrate it using nitric acid and sulfuric acid mixture in their concentrated form. As they are ortho-para directing halogens, ortho is already black, the nitro group come and sits at the para position to the chloro group. If I reduce this nitro group, I'll get amino using a reducing agent like hydrogen or palladium. Then I treat with propanoyl chloride, I'll get the propanil weed killer. This is the approach we follow. This is the strategy we follow for one group disconnection, which is having two parts and connected through the heteroatoms. One more example I can give, chlorbenzide. I can cut over here or cut over here. If I cut over here, this part represent this S is electron rich, heteroatom S minus, and this CH2 it gets plus charge. Or if I disconnect it over here, S gains electron richness, and this becomes positive center. But however, S minus, it can act as a nucleophile, and nucleophilic substitution of the benzene ring is a difficult task because of the fact that both benzene ring and the sulfur anion are electron rich. They are like poles. Like poles repel each other. That's why this is not the right way of disconnection. The first one is the right way of the disconnection. These synthons, the first one, I can use corresponding mercapto derivative of chlorobenzene, and here CH2. Here I have plus. To get plus, I add an easy leaving and electron withdrawing group, the halogen. The chloromethyl derivative of chlorobenzene. The sulfur has lone pair of electrons. It attack on the positive center. Chlorine gets kicked off. I'll get chlorobenzide. Adjacent to the heteroatom, I'll break. This is the strategy followed for CX disconnection. Whenever any molecule has two parts and is connected through an heteroatom, we disconnect at the CX junction, such that we get the two synthons, and the synthon reagents responsible for those synthons are selected and are taken into consideration for reaction. Another problem which we see in this, two groups are there in the single molecule and both are reactive, there arises a chemoselectivity. For example, there is carboxylic OH group and phenolic OH group, both are equally reactive. Then both will react. I want only one OH group to react. Then how to overcome this chemoselectivity problem? When it has two groups which are different in nature and they have different reactivity, then I can choose the reaction condition that only one group will react. If both are equally reactive, how to do that? When we do the disconnection, we have to select a synthetic route such that the chemoselectivity problem is overcome, or there is no chemoselectivity problem at all. In practice, when this arises, we will disconnect the one of the reactive groups and make the other group react, and then add the another reactive group. I can explain this by using the retrosynthesis of cyclomethane, an anesthetic agent. This is cyclomethane. Here there is an heteroatom oxygen, and this is one part and this is another part attached to it, and I do CX disconnection, CO disconnection. Here I'll get corresponding benzoic acid derivative. Now this is having two parts. One is cyclohexyl group, another is benzoic acid group attached through an heteroatom. I'll do CX disconnection over here. If I break over here, one part will be para-hydroxy benzoic acid, another part will be cyclohexane. To make this react with this, I have to create a positive center on this cyclohexyl group. That's why I add an easy leaving an electron withdrawing group like iodide, cyclohexyl iodide. This has lone pair of electrons, oxygen, as it is in the sp3 hybrid form, it can attack on the positive center and iodide can get kicked off, and I'll get the corresponding cyclohexyl group joined through this oxygen to the benzoic acid group. However, here you see there is OH, phenolic OH and carboxylic OH. Both are equally reactive. The cyclohexyl iodide can react with this OH and also with this OH. How to overcome this? Here this is a carboxylic OH group, this is a phenolic OH group. Though they are OH group, but one is phenolic, another is carboxylic. Carboxylic are more acidic, phenolic compounds are weakly acidic. That's why we go for preferential reaction conditions such that only the phenolic OH group reacts. How we can approach? What strategy we can follow? I'll take benzoic para hydroxybenzoic acid. I use excess base. When the base I use, that base abstract the proton in the OH group of COOH and the proton in the OH group of the phenolic OH, both get abstracted and both will be equally reactive. When the pH is above 10, to make only the OH reactive, this phenolic OH reactive get ionized, I'll keep the pH of the reaction at base such that pH is below 10, such that only phenolic OH group is ionized and the carboxylic OH group is in unionized state. When only phenolic OH group is ionized, it reacts with cyclohexyl iodide and the cyclohexyl group attached to this oxygen. Right. And then I treat with dialkyl amino propanol, and here I treat with thionyl chloride such that it becomes COCl. Cl is an easy leaving group. OH attacks on this carbonyl and HCl goes away and I'll get the cyclomethykyne. Here the pKa of phenol is equal to 10 whereas benzoic acid is 4.20. This difference in this pKa values I utilize to ionize only phenolic OH, such that phenolic OH only reacts, the carboxylic OH do not react. This is the strategy which we follow when two same type of groups are available but with different reactivity. We optimize the reaction condition. Here we have optimized the pH such that only the phenolic OH group gets ionized. Now you can appreciate the utility of the maintenance of reaction condition. The reaction condition selection is a important task and also a strategy to overcome this chemoselectivity problem. I can explain this by using another molecule, the synthesis of paracetamol. Paracetamol, as the name indicates, it is para hydroxy acetamol. Para amol में all OH. Para acetamino phenol is paracetamol. This is having two parts. One is acyl group, another is phenyl group attached through an heteroatom where I can carry out CX disconnection. Adjacent to the heteroatom, I disconnect over here. I'll get para-aminophenol. The amino group is in nitrogen here, is in sp3 hybrid form, and it has a set of lone pair of electrons. OH is also an sp3 hybrid from it has two sets of lone pair of electrons. These excess electrons which amino group and OH group both are having can be donated, and when I carry out acetylation, N acylation can occur and also O acylation can occur. That's why I want only the amino group N to get acylated, not the OH group. But both are reactive. In this case, what should I do? Anyhow, amino group directly I cannot attach because NH2 minus is electron rich and nucleophile benzene is also electron rich and like poles repel each other. Hence, I do fragment group interconversion. Instead of NH2, I will add nitro group. I'll do CN disconnection and I will get phenol. I'll follow this strategy for the synthesis of paracetamol. I'll take phenol and treat with concentrated nitric acid and sulfuric acid mixture. OH, as it is orthopara directing, and para will be the major product, and I'll get corresponding para nitrophenol, which upon reduction with hydrogen and palladium I'll get corresponding para aminophenol. Now amino group is reactive, OH group is also reactive. I have to carry out acylation and I should get only para acid aminophenol. The amino group should get acylated. Here the OH, if I keep it in unionized form, then the NH2 will react. As oxygen is more electronegative, though it has two sets of lone pair of electrons, because of its basic electronegative nature, it won't donate so easily. Whereas amino group is comparably less electronegative than oxygen. The nitrogen is less electronegative, that's why it is more free enough to donate those lone pair of electrons. When I keep it in the unionized stage, the NH2 group is more nucleophilic. If I make it ionized, the O minus will be more nucleophilic. There is pKa of phenol is 10, pKa of aniline is 30. And I add one drop of concentrated sulfuric acid such that this is not in the ionized form. It becomes, if I add one drop of sulfuric acid, it becomes OH2 plus, or it will be not be in the reactive stage, only the amino group will react. A drop of sulfuric acid makes amino group more reactive. Excess if I add, this also get protonated and it becomes unreactive. That's why careful pH maintenance over here make amino group more reactive than that of the OH, because OH will be in the unionized state. This is the strategy we follow. Another strategy what we can follow is that protect the group such that it do not, one group I will protect and make other group react and then deprotect. But however, it adds two more steps. One is protection step, another is deprotection step. Though it increases the number of steps, but when this reaction conditions choosing is not possible, then we go for protection approach. Another strategy is to protect one group and make another group react and then deprotect the other group. I can explain this by taking this molecule as an example. I have salicyl alcohol at meta position bromo, meta bromo salicyl alcohol. I'll do disconnection at the heteroatom position, CX disconnection, CBr. I'll get corresponding salicyl alcohol. Then I do fragment group interconversion. This CH2OH directly I can't add, that's why I will take COOH. I get salicylic acid is easily available. Here, when I carry out the synthesis, I'll take salicylic acid as the starting material, treat with lithium aluminum hydride. As we know that it is a good reducing agent, the carbonyl group gets reduced to corresponding alcoholic group to give corresponding salicyl alcohol. When I brominate this, I'll get this OH is ortho para directing. Ortho is already blocked. That's why they direct the incoming group bromine towards para position. CH2OH. This is OH is direct towards para position, and that's why I'll get the bromo group attached to this. But however, bromine is also an oxidizing agent. Along with this meta bromo salicyl alcohol, I'll get this corresponding salicylaldehyde as a byproduct. The CH2OH, yes, is a bromine is a mild oxidizing agent. It oxidizes to corresponding aldehyde. It not only undergoes substitution, it also acts as an oxidizing agent and oxidize this alcohol to aldehyde group. Here the bromine duality of nature is the culprit. Like we are having good qualities and we have also bad qualities. The bad quality here is that it also acts as an oxidizing agent. How can we overcome this? We protect this OH group such that it won't get oxidized. How will we do this protection? That's why we revised the synthesis like this. I'll take salicylic acid, treat with lithium aluminum hydride. I'll get salicyl alcohol similar to the first step what we have done, and I'll protect this 2 OH group by treating with acetone in the presence of paratoluene sulfonic acid is a dehydrating agent. This acetone reacts with this OH 2 OH group and it blocks to give isopropylidine derivative. And this is not in the OH, this is in the ether form and this becomes unreactive. I treat with bromine, bromination occurs, and once bromination occurs, then again I have protect this OH group such that this OH do not get oxidized like this. Again, I hydrolyze this in the presence of an acid. Isopropylidine groups goes away. I'll get corresponding salicyl alcohol derivative. By protecting these two OH groups reaction, I made bromine to react with this benzene. But I have added one protection step, another deprotection step. The two-step synthesis has become 4. But however, I got pure product. Here 50% may be this and 50% may be aldehyde, X derivative. And this will, again I have to separate these two molecules. Instead of that, this will be better where I get very pure product. This is another strategy which we follow for the overcoming this chemoselectivity problem. Next class, we can deal with two group CS disconnection approach. Till then, have a nice day. Thank you.